Welcome to the Deep Dive. Today we're really diving into some fascinating sources about one of the most ambitious, maybe the most ambitious scientific projects ever undertaken, and the incredible discovery that came out of it.
It really is an amazing story.
Yeah, so imagine this, right? You're on a big science funding committee. Someone comes in, pitches this idea. We want to split atoms, find the basic rules of nature. Sounds okay so far.
Standard stuff, maybe.
Then they get you with the details. We need a machine, about 8 kilometers across.
8 kilometers?
Yeah, and it'll cost, let's say, $9 billion US.
Wow.
Plus, you need about 200 universities and labs from 50 different countries all working together for, maybe 30 years.
Okay. Yeah, you'd probably think they were joking or, completely out of their minds. It sounds like something from a movie.
Exactly, pure science fiction. But the amazing thing our sources show is this project, it actually happened. It's running now.
And it led to one of the biggest discoveries of our time.
The Higgs Boson, announced July 4th, 2012.
And what's really striking is how it broke out of just the science pages. It was everywhere, front page news, even in places like The Economist.
Right. Not your typical physics story location.
And of course, it led to the Nobel Prize for Francois Englert and Peter Higgs, two of the physicists who originally proposed the idea way back.
So that's our mission for this deep dive.
Yeah.
Why was this discovery such a huge deal? What even is a Higgs boson? And why on earth did it take this just monumental effort and grab so much attention?
Yeah, let's unpack that. It's quite a journey.
Definitely. Let's get into it. Okay, so thinking bigger picture first. When you look up at the Milky Way, you feel this need to understand, right? What is all that stuff? How do we fit in?
It's a fundamental human question, isn't it? Trying to find order in all the chaos and complexity.
And our sources point out this long history. Think ancient Greeks. They had this bold idea.
Yeah.
Maybe everything, all the variety in the world, is made of just a few basic things.
Earth, air, fire, water. They were a bit off on the specifics, obviously. But the core idea, that the drive for simplification, that was spot on.
Right. Fast forward a couple of thousand years, chemistry gives us the periodic table. Millions of substances. Boom. Down to about 100 elements.
Which is already an incredible simplification of nature, a huge achievement.
But we didn't stop there, did we? The sources show we kept digging deeper.
Yeah, and this is where it gets really mind-bending. You go deeper than atoms. What are they made of?
Okay.
It turns out that all the ordinary matter around us, I mean, the device you're listening on, the chair you're sitting in, you yourself, it's all made of just 3 fundamental bits.
Really?
Up quarks, down quarks, and electrons. That's it.
That's wild. It's like that movie, The Matrix, Yeah. Everything's just code, zeros and ones. Here it's just 3 particles.
It's surprisingly elegant, yeah. You'd almost expect nature to be messier at its core.
But it's not just about the stuff, is it? There are forces, too.
Exactly, you need interactions. And our sources explain how forces like light or electromagnetism, radioactivity, the weak force, and the strong nuclear force holding atoms together. These are also described by particle exchanges.
So, like, photons carry electromagnetism.
Precisely. And you have W and Z bosons for the weak force, gluons for the strong force.
So if you put it all together, this framework, the standard model of particle physics, it basically covers almost everything we observe.
Pretty much all fundamental processes, yeah. With just 16 basic components when you count them all up, the matter particles, which scientists call fermions, like quarks and electrons.
And the force carriers, the bosons.
Exactly. 16 particles to explain almost the entire physical universe at its most basic level. It's an extraordinary intellectual achievement.
Okay, so this model, the standard model, sounds amazing.
Yeah.
Describes everything perfectly.
Almost. It worked incredibly well, predicted things with amazing accuracy. But there was this one gigantic problem that really came into focus around 1964.
A problem? What was it?
According to the mathematics of the model, the only way it worked consistently was if every single one of those fundamental particles had 0 mass. None at all.
0 mass. But things have mass. I have mass. This desk has mass.
Exactly. That's the problem. But maybe let's quickly recap what mass even is fundamentally.
Good idea.
Mass is basically inertia. It's how much an object resists being accelerated when you push on it. It's the resistance to converting energy into motion.
Okay, like imagine a bowling ball and a beach ball. Same size, maybe same color. You give both the same little tap.
Right. The beach ball goes flying. The bowling ball barely moves.
Because the bowling ball has more mass. It resists that energy input more.
Exactly. Now, here's the crucial bit. What if something had zero mass?
Oh, no resistance at all.
None. Any tiny bit of energy, no matter how small, would instantly accelerate it to the absolute maximum speed possible in the universe.
The speed of light.
The speed of light, always.
So, the problem in 1964 was that the best theory we had said all fundamental particles must have zero mass, and therefore must always travel at the speed of light.
That was the prediction, which we clearly know isn't true. Electrons orbit atoms. They don't just zip off at light speed.
Why does that matter so much?
Yeah.
It's wrong, but what are the consequences?
Well, the consequences are everything. If electrons did have zero mass and always flew at light speed.
They couldn't be captured by atomic nuclei.
Exactly. No atoms could form. No atoms means no molecules, no chemistry, no stars holding themselves together properly, no planets, no biology.
We lost.
No us. The universe would just be this soup of fundamental particles whizzing around at the speed of light, unable to form any structures at all. It would be radically different. You wouldn't be here listening.
Wow. Okay. So that's a pretty big problem for your beautiful theory.
Understatement of the year, yeah. A fatal flaw,
Unless it was a fix.
unless there was a fix. And in 1964, 3 different teams of scientists independently came up with an incredibly bold, almost, well, audacious solution.
What did they propose?
They proposed the existence of something completely new, a quantum field spread throughout the entire universe. A field whose specific job was to give mass to elementary particles.
A new field? Just for mass? How would that even work?
Okay, there's a great analogy for this, often credited to Professor David Miller. Imagine a big room packed shoulder to shoulder with political reporters. That room full of reporters represents this new field, the Higgs field.
Okay, got it. Crowded room, Higgs field.
Now imagine a very famous person, say Albert Einstein, tries to walk across that room.
Right, he'd be mobbed. Everyone wants to talk to him, ask questions.
Exactly. The reporters cluster around him, making it really hard for him to move. He has to expend a lot of energy just to move slowly. He feels a lot of resistance.
Like he has a lot of mass, like the bowling ball.
Precisely. His interaction with the field of reporters gives him effective mass. Now, imagine someone completely unknown walks into the same room.
Nobody cares. They just walk straight through.
Right. No resistance. They can move easily, quickly. They essentially have no mass in that context.
So mass isn't something particles have intrinsically like charge. It's about how they interact with this Higgs field.
That's the revolutionary idea. Mass becomes an emergent property from the interaction with this background field. Different particles interact differently, some strongly, like Einstein, getting lots of mass, some weakly, getting little mass, some, like the photon, maybe don't interact at all.
And stay massless, moving at light speed.
Okay.
That makes sense.
But there's another part to this analogy, another consequence. What if, instead of a person walking in, someone just whispers a rumor near the door, like, hey, free donuts in the lobby?
Okay.
That rumor would spread through the room, right? Reporters telling other reporters. It creates a sort of ripple, a disturbance in the crowd itself.
A wave of excitement passing through the reporter.
Exactly. That ripple, that exaltation of the field itself.
Yeah.
That's the Higgs boson, not like a particle in the field. It is a quantum vibration of the field.
A particle that is the field waving.
In a manner speaking, yes. And it has unique properties, unlike all other fundamental particles. It has zero intrinsic spin. It's a scalar particle, which is also something quite new, theoretically.
This field.
Yeah.
It's everywhere. You said the entire universe.
That's the idea, pervading everything.
Yeah.
From here to the edge of the observable universe, from the beginning of time potentially to the end, it's even right here, inside the atoms that make you up, in the empty space between the nucleus and the electrons.
That's hard to grasp. Most fields, like magnetism, drop off as you get further away from the magnet, right?
Right? Other quantum fields, like the electron field, are basically zero unless there's an electron present. But the Higgs field, the theory proposed it has a non-zero value everywhere, all the time, even in the vacuum of space.
Just constantly there.
Constantly there. Providing the potential for mass, postulating something like that, this invisible, ubiquitous field.
Yeah.
It was, as one physicist put it, uncommonly daring.
Uncommonly daring. I like that. It sounds elegant mathematically, I guess.
It was very elegant, solved the mass problem beautifully within the standard model framework.
But as our sources stress, just because math is elegant doesn't mean nature actually uses it.
Absolutely. Nature could have found a different way to give particles mass. Mathematical beauty isn't proof.
So the only way to know for sure
Was to find it. You
Yeah,
find the observable consequences, and the most direct consequence of this field existing was the existence of its particle, its ripple,
the Higgs boson.
the Higgs boson. If you could find that, you'd know the field was real.
Okay. So you have this theory, this prediction of a new particle.
hmm
How do you even begin to look for something like that? Especially if it's, related to this invisible field everywhere.
Yeah, it's not like you can just, scoop up some Higgs field. You need to actually create the Higgs boson. And to do that, you need, well, basically three things.
Okay.
One, you need a way to produce the particle, which means you need incredibly high energies, conditions like the very early universe.
Right, like smashing things together really hard.
Exactly. Two, you need detectors, really sophisticated, enormous detectors, capable of spotting the faint, fleeting decay products of a Higgs boson if you manage to make one, because it doesn't live very long.
Okay, makes sense.
And three, you need computing power, just staggering amounts of computing power to sift through the debris of those collisions and find the tiny signal you're looking for among billions of other events.
That takes us back to the beginning, that crazy 8-kilometer, multi-billion-dollar machine.
That's precisely what it took. That machine is the Large Hadron Collider, the LHC, built at CERN.
CERN, the European Organization for Nuclear Research near Geneva.
Right. And, thinking about the sheer human effort, CERN itself is an amazing story. Founded back in 1954, originally 12 European countries.
Now many more member states, plus collaborators from all over the globe.
Yeah, it really shows how science can overcome national boundaries and skepticism to achieve something immense. Getting hundreds of institutions from, like you said, nearly 50 countries to work together for decades is just incredible.
So they built the LHC, 27 kilometers in circumference, buried underground. The biggest machine ever built.
The most powerful particle accelerator, smashing protons together at unprecedented energies up to 14 trillion electron volts eventually.
Trying to recreate those Big Bang conditions.
Essentially, yes. And alongside it, these gigantic detectors, ATLS and CMS, huge complex instruments like multi-story digital cameras designed to track every particle flying out from the collisions with incredible precision.
An absolutely monumental undertaking.
Decades in the planning and building. And finally, after all that effort, July 4th, 2012,
The announcement.
the ATLS and CMS teams presenting their data side by side, both showing clear evidence for a new particle with properties consistent with the long-sought Higgs boson, they'd found it.
Wow. Decades of theory, decades of building, global collaboration, all culminating in that moment.
A truly historic day for science.
So let's tie this all together. What does finding this one particle, the Higgs boson, really mean? Why was it worth all that?
Well, it's not just about finding a particle. It was about confirming this whole theoretical structure that explains something incredibly fundamental.
Why things have mass.
Why things have mass, which, as we discussed, is essential for everything. Without mass, particles would just fly around at light speed. No atoms, no structure, no chemistry.
No life, no listeners.
Exactly. The Higgs mechanism, confirmed by finding the boson, provides the reason why the universe isn't just that thin, structureless soup. It allows for complexity for us.
So it validates that uncommonly daring idea from 1964.
It does. It shows that this pervasive, invisible field is likely real, shaping the universe at its most fundamental level. And it was the capstone, really, of the Standard Model, the final missing piece.
A triumph of theory, engineering, and just sheer human collaboration on a global scale.
Absolutely. A testament to decades of ingenuity and persistence.
But, and there's always a but in science, isn't there?
Usually, yes.
Our sources hint that, as amazing as this is, it's not the end of the story. The Standard Model, even with the Higgs, isn't complete.
That's right. It doesn't include gravity, for one thing. We still don't have a good quantum theory of gravity that fits with the Standard Model.
And things like dark matter, dark energy. These huge cosmological mysteries aren't explained either.
Nope. The Standard Model describes the ordinary matter, the stuff we see, incredibly well. But that seems to be only about 5% of the total energy and matter in the universe. There's still a lot more out there we don't understand.
So the Higgs discovery was monumental, but it also sort of points towards new questions, new physics, beyond what we currently know.
Precisely. It completes one chapter but opens up the next.
Which leads us to a final thought, maybe for you, the listener. If something as basic as every day as mass required this incredibly subtle, universe-filling field, something completely unexpected back in the day to explain it,
Yeah.
what other hidden mechanisms, what other invisible fields or undiscovered principles might be operating right now, underpinning reality in ways we haven't even imagined yet?
That's a great question. What other uncommonly daring ideas are out there waiting for their own LHC, their own moment of discovery that could completely change our picture of everything once again?
Something to think about.